Hey guys, my name is Matt and I love both cars and new technology. Recently I decided to replace my halogen headlight bulbs with LED retrofit bulbs. I discovered a whole new world. Automotive LEDs are designed according to specific and different standards, so you can see and be seen perfectly at night, like the Philips LED retrofit. But what's an LED retrofit bulb? Well, to answer that question, let's give the floor to Mark Kessels. He's an expert in LED technology, and he will lead our way today.
An LED retrofit bulb is a lamp designed in such a way as to imitate a halogen bulb, and thus allows you to replace your halogen headlight bulbs. This upgrade offers better control of the light, an Arctic white light and a clean beam pattern that does not glare on oncoming drivers. Of course, even if LED retrofit bulbs somehow behave like halogen bulbs, they are not built the same way. Let's have a close look. An LED retrofit bulb contains, as its name already states, an LED. This is the light engine of the bulb. For our bulbs, such as the Philips Extreme Ultron, we are using Lumina's automotive grade LED chips, otherwise only available to car makers. It provides a bright and uniform beam in a cool white color temperature. The LED chip also provides excellent thermal performance in order to operate at high temperatures. Speaking of heat, this part is called the burner. Every source of light generates heat. Even though LED retrofit bulbs produce light more efficiently than halogen, they still produce heat. LEDs will live longer if they are working at lower temperatures. Therefore, it's important to move the heat away from the LED light engine as quickly as possible. And this is where the design of this burner comes in. It moves the heat away from the LEDs into the heatsink. A good burner uses materials with high thermal conductivity. The next mechanical part is the heatsink. Now the heat is moved away from the LED, but it still needs to be transferred to the ambient air. And this is done with a heatsink. Our LED retrofit bulbs feature Philips heat management systems, which can be passive or active. This Philips LED H7 is using an active fan-based cooling system. The heatsink is small and very powerful at the same time, and that will ensure a reliable lifetime. To switch the bulb on, we need some electrical components. This robust cable connects the bulb to the car electronics. It's highly reliable for enhanced safety and performance. Some bulbs also feature an external driver. This driver ensures a constant light output through the LED, because any slight variation in the current could result, for instance, in loss of brightness. The driver also powers the fan in the heatsink. Now we have a working bulb, so let's mount it in a headlamp. This part here is called decentering. It ensures the right positioning of the LED retrofit bulb within your headlamp. We want to make sure that the LEDs in the bulb are at the same position as where the filament is located in the halogen bulb. By turning the ring, we can make sure that the LEDs emit the light sideways so that we get the best performance on the road. And here it is.
Wow, I mean, so many components for a small device. It's fascinating, isn't it? Well, the Philips LED retrofit bulbs are also very robust. They can withstand severe vibrations and are EMC verified, meaning they won't suffer from any interferences of your car's other devices. I got one last question though. How does an LED retrofit bulb work? I mean, it's not a very hot wire, as in halogen bulbs.
LED stands for light emitting diode. It works thanks to an electrical reaction. And the key word is diode. It consists of two layers of semiconductor material made of indium gallium nitride. One semiconductor is doped with negative particles, providing electrons, and the other one with positive particles, holes, which absorb electrons. When connected to one another, they create an electrical diffusion layer where the positive holes absorb the negative electrons. When a hole merges with an electron, light is emitted. By attaching a battery to the LED, new electrons and holes are pushed into the diode, so we keep getting light out the diode. See? It's easy.
Even my physics teacher couldn't have done it better. Thanks, Mark, for everything. Thank you guys for watching. That's all for today, but we'll be back soon and ready to lead your way.
Innovation and you, Philips.
Hey guys, it's Matt. Today's episode will be filled with colors. Indeed, I'd like to know more about that white light LED bulbs produce. How's it done? What's the process? And I realize that to answer that question, it is key to understand more about the LED technology. Today's expert is Mark Kessels, and he will lead our way.
As you may know, LED technology is truly fundamentally changing the lighting industry. But how is it done exactly? Well, it all starts with a wafer of dyes. The wafer itself is made of thin layers of semiconductor material, which are the core of LED technology. It's then cut into many small pieces of 1 square millimeter that we call dies or chips. The die is then encapsulated in a package. A package allows to direct the light and protect the chips from being damaged. You may have heard of several packaging techniques such as CSP, SMD or COB. Let's dive into that. A COB or chip on board has literally its chips being mounted on the board. A COB also has a large number of light-emitting diodes inside. It's known for its better efficiency and it is nicely distributing heat. However, it makes projecting the light more challenging. As the light-emitting area is very large, in optical applications like automotive headlamps, we want to have the source as small as possible, for it creates the sharpest beam with the longest range. And with a COB, it's impossible to recreate the optical fit for headlights. You may also encounter some lens-type LED packages with a dome on top of the chip. The dome itself increases the light output of the LED, but it also works like a magnifying glass. As you can see in this mock-up, when I remove the dome, the chip is much smaller, and the dome thus makes the LED virtually larger. And that's why we are not using either COB or domed LEDs for automotive lighting technology. Eventually, as LED packages are made smaller and slimmer, the CSPs have been developed. This goes for chip-scale package. And those packages are almost equal to the size of a die and offer higher flux, luminance and contrast ratio. And CSPs are, for example, also integrated in your mobile phone. Once the package is finalized, it's soldered to a carrier board that we call a printed circuit board or a PCB. Put simply, it's a board with an electric circuit included. When properly connected, the chips light up whenever the circuit is connected. SMD goes for a surface-mounted device. Those LEDs are the most common on the market. The LED is soldered on the PCB, which ensures a good electrical and thermal contact between the LED and PCB. These chips are our first choice when it comes to Philips LED retrofit bulbs. Our latest generation feature exclusive Lumileds Luxon Ultron SMD LEDs. Specifically developed for front lighting at car makers, these chips produce a superior reliability, beam intensity and uniformity in color. This is where we intervene. We assemble the chip with some automotive elements, such as the heatsink, the burner, add a cable, the driver, and actually we created an LED retrofit light bulb. The LED retrofit bulb can be inserted into a headlamp and then into a car.
Wow. I mean, the making of an LED is a really complex process. But the good news is, We now have all the information we need to understand how that white light is produced.
Depending on the semiconductor materials used, LEDs produce different colors of light. For example, blue, green, or red. And by mixing the right colors, white light can be made. Another way to make different colors is by using phosphor materials. Like this. Phosphor converts one color of light into another color of light. In automotive LEDs, we use yellow phosphor layer on the blue chip. As a consequence, when the blue light hits the phosphor particles, they glow and emit yellow light. This process is called fluorescence. Combined with transmitted blue light of the LED, it results in white light.
So white light is thus a mix of various colors. It can also be produced by combining red, blue, and green LEDs by varying the intensities. Thank you, Mark, for sharing these fascinating techniques. You now know, guys, everything. That's all for today, and I hope this episode will help you lead the way.
Innovation and you, Philips.